Good morning, everybody, and welcome to week 6 of physical science. Today is October 10th. So we're building up materials for the upcoming exam, and actually we are right in the middle, basically, of where we're supposed to be. So this week, we're going to be covering 2 topics, namely, and that is the circular motion and also the projectile. So those are the 2 topics we'll be covering this week. And they're important topic because up to now, when we started basically all of this chapters talking about mechanics, especially, namely the 3 laws of Newton and so on and so forth, we were talking really in 1 dimension, mainly motion on a line. Think of it as if you have a string, for example, where you have beads attached to it, where they can move on that line. So that is really what the motion in 1D is. I mean, in the first approximation, what you could say is, for example, a car moving on the freeway. As long as the freeway doesn't curve one way or the other, or doesn't have any bumps, basically this could also be described using the laws that were discovered up to this point. But this is really an idealization. This is not really what the real world is. The real world has motion in more than 1D. And this is a very powerful approach to science in general, to life in general, not just physics or this particular part of this class. And that is when you're trying to learn or trying to solve a problem in real life, the way you approach it is basically by doing it like making it as simple as possible without loss of how should I say, a critical piece of information in it. And then solving that part. Once you do that, then you start embellishing it. Then you start adding more and more stuff to make it more and more realistic. So if you're at work, for example, and you have a new challenge and they ask you, for example, to come up with a plan, the first thing to do is actually, instead of having to focus on those side effects, if you wish, or side stuff, you just want to make the bulk of it. And this is exactly what we did up to this point. So we wanted to understand the motion in general. So what we said in here, instead of really looking at motion in the most generic case, which is going to be complicated, we made it into 1-dimensional line, basically, on like a number line that you guys are familiar with from the math classes. In addition to that, we really did not want to take the object and make it as complicated, because objects come in different shapes. You have spherical objects, you have cubical objects, you have objects with no shape, like a potato, for example, and you have objects that weigh a lot and objects that weigh less. So we wanted to make it as simple as possible. And really what we were talking up to this point is the so-called point particle. So what a point particle is a mathematical point that carries the entire mass, because mass is important when we're talking interactions and mass, and gravity, and even inertia. So all of these things, they come into, mass comes into play, and they're important. So we didn't really eliminate objects altogether. We made them as simple as possible, and namely objects with no dimension. So we were not really worried if they were spherical or not. We were not worried about how much contact that they have with the surface or not. So we were trying to make them as simple as possible, and then studying them on a 1-dimensional line. So this is really where we were. Now we want to move on. We want to explore more realistic, more complicated situations. So the first step we're going to go is move from the 1-dimensional objects, namely objects moving on 1 line. We want ultimately to go into a multi-dimensional motion in more than 1 line. It could be on a plane instead of a single line, or it could be in space. So that is probably the most general case that we're going to talk about, motion in space. But even that's still complicated for us. So we're going to go into a 2-dimension initially. Ultimately, we're going to go to a multi-dimension. So this is basically the plan. So let me get into my notes and see exactly how this works. And before I do that, let me share with you, first of all, guys, this week, so that you guys have, we're going to have a glimpse into what we have this week, so that you guys see what's going on. share. So what we have this week, of course, we have the objectives and we have the two types of motion that we're talking about, namely the circular motion and the projectiles. There are a couple of videos in there. They're kind of short, basically combined. They're less than 20 minutes, so you should be able to go through them quickly. You have a quiz at the end. So this has been like the habit so far. You have the discussion with rubrics, and it's due October 22nd, which is not this Sunday, but the Sunday after. 22nd is Sunday, or is it yeah, it is a Sunday. Yeah, it was intended to be a Sunday. Very good. So it's on a Sunday, October 22nd. And then we have been having labs every single Monday. Today, for example, at 12:45, we're supposed to have labs. This week, we are going to have a very, very important session where we're going to be discussing those problems basically and more, the ones that we've been assigning as homework. As a matter of fact, for those who don't have the book or the hard copy of the book, at least I scanned the problems in here and I posted them for you guys on this link. So you should be able to download them. If you don't have the book, if you do have the book, you just need the pages, that's all. Okay, whether the book online or printed, doesn't matter. All you need to get is those pages, which are the exercises from the end of each chapter, namely chapter 2, 3, and 4. So those are the stuff that we're going to be covering this week. And they're of extreme importance that you guys attend the lab and we go through them all and make sure that you guys understand how to do things like this, so that if in case, and it's not if in case, there will be problems of the same caliber in the exam 2. So you really need to be ready for exam 2 by practicing those problems, by understanding how to do them, because come exam 2, you're going to have problems similar to the problems we're going to have in the discussions in here, and you should be able to solve them. So exam 2 has two components, has a component similar to exam 1, where you basically have multiple choice questions. We're going to go and basically review them and prepare them in a similar fashion that we did with exam 1. However, exam 2 has a second, it's a two-parter exam, basically has a second part in it. And the second part deals with this type of questions, basically, where you're going to have an open statement. So you're going to basically answer the question and solve it and basically post them either as an image after you do it on a piece of paper, or actually solve it on Canvas and go through the steps and show me the steps and give me the answer to these problems. So this is something that I want to bring to your attention, because today at 12:45, we're meeting on campus. That's our regular hour anyway. We're supposed to meet there anyway. So this is not something new. So you guys are supposed to be there anyway. And this is the session we're going to be covering is the problems in here. And it's dated 10/10, which is October 10th today. Okay. Then we have the homework assignment in here. I know there was a buildup of homework leading up to this point in here. And the homework up to this point in here is actually going to require 2 problems, not 1, 2 problems for submissions for a grade. You're required to do all of them, by the way. It's not like you have an option. You have to do all of these problems from this page, okay? Now, you're required to submit 2 problems for grading. One of these problems must be either 59 or 60. So either this one or the other one. They're a requirement, okay? These are required. And then in addition, another problem. So you have to have 2 problems. One of them must be 59 or 56, not both of them, either one or the other, okay? So once you have one of this, you decide, okay, I'm going to submit 59, then pick and choose from the rest, either 56, 51, 57, 58, 61, 62, 65, or 66. So this is really the exam. Again, the rubric is below for both problems and how they're going to be graded. The required one and the non-required from the list, but it's still required. So both of them are required, okay? So you're required to submit 2 problems nonetheless. One of them must be from one of these 2 options. So I hope this is clear so that you guys understand what's going on in here. Let me try to go back for this week, 6. So that we have that. And again, we have the live session of recording for today and Wednesday. They're going to be posted in here. So this is just the stuff that we have from this week. We have, of course, the discussion that is also graded, due October 22nd, and also the homework assignment, which is October 22nd. Don't forget you have other stuff from the previous week. Homework 4, for example, which is due from last week. And then you also have discussions from last week. This exam, of course, was done already, so we're not worried about that part. So this is the stuff that we have up to this point. And I really want you guys to be aware of it. By far, this part of the class is probably the most important part in the entire course. So understanding Newton's laws, understanding how they apply, it is a critical piece of what you need to take from this class. So that's why the emphasis is on it. There will be down the road stuff related to electricity, which is also of extreme importance that we're going to be covering. But at this point, by far, this is the most important thing that you're going to take from this class. And that's why it's important, and it's tested, and you're going to be doing problems with it, and you're going to take stuff to the next level. So let me share the screen again for my what is it? Yeah, for my notes. Okay, so we're in chapter 4. And before I start chapter 4, let me just remind you quickly on what happened up to this point. So again, we're dealing with a point particle of mass m, and we said that this object moves on a line. So we could take an origin somewhere and then start labeling the position of this particle. Usually we give it the letter X symbolically. So this is a symbol of the position. The position could be a positive or negative on this axis. So we're not really worried about vectors per se, but it's really a vector place. So this is a position, and position usually has some sort of an origin and unit also of measurements. In other words, how many meters is it from the origin? How many kilometers is it from the origin? How many miles is it from the origin? And so on and so forth. So you really need the unit of measurement and compare that to your standard, the ruler that you're using. So in this situation, probably 1, 2, 3, 4, and maybe even 5 units from the origin. So if this were a meter, so if this is a meter, then it's really 5 meters. If this was a kilometer, then this is 5 kilometers, and so on and so forth. So this is the position. It could be a positive or it could be negative. In other words, was it behind the origin on the left side, or is it on the right side? That's really what that means. For example, we take I-10 as an example. We say, is the object on the right-hand side, or is it the LA side? Compared to some starting point, let's say, for example, the intersection with the 215. That is being the origin. Then anything on one side will be positive and the other side will be negative. And the choice of positive or negative is really arbitrary. We could decide, in my case in here, which is a convention really, we put the right-hand side to be positive. It doesn't have to be. Any direction of your choice is really your choice, okay? But the other one, you have to really account for that direction. Then we came up with the velocity, and we said that that's the rate at which this X is changing, the position is changing. So this is the change in position. So when you see the delta in here, that means change. Over the change in time, basically the lapse in time. So when you see the delta again, that's the change. So again, this is the lapse in time. In other words, we're not really concerned about the time per se. We're concerned about how much time lapsed in covering that distance. That's really what we're concerned about. We don't care when that event happened. We care how long ago since a previous event taken place. So what we do in this case is we take the position of the object, we could label it x1 at t1. So at some point, the object was somewhere. At some later time, the object is in a new place, not necessarily the same place as before. So this happened later on in time, and this happened earlier in time. So the difference between these two is what I call delta t, the change in time or the lapse in time. Delta x also is a displacement, in this case, in space. The ratio of these two is what we define to be velocity. Now, the velocity could be positive or negative. In other words, we could be gaining more and more in the positive direction positions. It doesn't mean that we are in the positive direction. We could have been in here, for example, at negative 1, 2, 3, 4, negative 4 meters earlier, but 2 seconds later, we are at negative 2 meters. So we're still in the negative side, but we gained if it is positive. If it's negative, we lost. So that's what the delta x and the delta t also mean. The delta t typically is positive, but it could be also negative if I'm trying to go through the historic story of this object, basically what happened to it in the past. So you could do it also in a reverse order for the time too. So this is the velocity. This is by definition the velocity. And this is actually an average velocity as opposed to instantaneous velocity. If the time lapse is very small, as close as possible from zero, but not zero. Because if it's zero, then the object would not have moved. Because if the time doesn't change, the object is somewhere specifically, okay? So, but with time basically is allowed to tick even a fraction of a second, then the object theoretically could have just moved. So in that situation, it has a velocity. In that instant is what we really mean by an instant velocity. So this ratio is in general for the average velocity, okay, unless delta t is very small. So what I mean by this symbol, which is used in math a lot, is delta t is small, very small. That's what that means, okay? Okay, so that's basically what that symbol is. So don't be too turned off by it because it really doesn't mean much more than that. Very, very small quantity. Then we define the acceleration as the rate at which the velocity also changes, delta v, with time. That too has two meanings. This is really the average acceleration. So this is the acceleration. And in the sense that the lapse of time also is very small, that too means the instantaneous acceleration. So the acceleration and the velocity is the rate of change of position. The acceleration is the rate of change of velocity. So this is the rate of change of velocity. Note the following, and it's very critical in the previous chapters, that the velocity can only change one way, and that is by either increasing or decreasing. So in one dimension, the one that we were discussing earlier up to this point, in one dimension, by the way, sometimes instead of writing this whole thing, we write it just in 1D, okay? So if you see 1D, that's exactly what that means. So in one dimension, the velocity can increase So in this case, really, we say the object is accelerating. Or on the other side, velocity can also decrease. I mean, technically, it can stay the same, but if it's the same, that's really a trivial motion. If the velocity stays the same, then in this case, the acceleration is zero, because if the change in velocity doesn't happen, that means delta v is zero, so the acceleration is zero. So that is also another case too, if you want to. So the velocity can either increase or decrease, and that's the only way it changes. This is how velocity changes. No other two ways in 1D. No other way. No other way. Period. End of the story. Okay, I wrote it all in caps, meaning that I'm screaming when I'm typing it, okay? So that you guys understand how this is the case. However, in more than 1D, we have another possibility. So this is in 1D. In multidimensional motion, in multi-D, I mean multidimensional. In multidimensional motion, really, what I really mean by it, either a 2D or a 3D. Okay, so that's really what I mean by it. So there are actually many ways for the velocity to change. Either increase or decrease, like before. So another way that the object could gain more velocity or loses more velocity, that will result in a change in velocity. Or turn clockwise. You know how the clock goes? It goes from basically 12 to 1 to 2 to 3 to 4 to 5 to 6 all the way to. So you could go with the clock, okay? How the clock goes, or against the clock. I mean, the clock goes like this. At least for me, probably when you look at it, because it's reflected in your screen, you might see it in the opposite direction. So it's going like this. That's how the clock goes. Or you could be going in the opposite direction, basically against how the clock goes. So those are many ways for the velocity to change. Okay. So it's not just by, it could retain its value. So the magnitude stays the same in this situation. Mag, same. In other words, the object speed is the same, but it's turning left or right. Mag also speed is the same. And here, in the first two cases, the speed is actually changing. That is a big critical difference. So in a multidimensional case, you are not just worried about the value if it's getting bigger or smaller. You're also worried if it is the direction is changing. That's basically what that means. Okay. So it could happen all of them in the same time. The object could be speeding up and turning left, or slowing down and turning left, or speeding up and turning right, or slowing down and turning right, or keeping its speed and turning left, or keeping its speed and turning right. So as long as any one of these conditions is met, the velocity changes. So the bottom line, in a multidimensional motion, the velocity could change in magnitude and or, so both of these are possible, direction. As long as any of these situations is there, now we have acceleration. So there are two types of acceleration. Then this is immediately, because acceleration accounts for the changes in velocity. Acceleration is the one that tells you how the velocity is changing. So there are two types of accelerations. Tangential acceleration. And this accounts for the increase or decrease in velocity. This accounts for the magnitude. Okay, and there is something else called now, as opposed to tangent, which is the normal to the tangent. I'm going to draw the shape in here so that you guys see it. Think of a circle or parts of a circle. So here is the path of the object, and there is a center of curvature somewhere. So this is the center O, and this is the radius of that center. So think of it as a big circle of radius R. So in this case, the object could be accelerated. So this is its velocity. The velocity is along the tangent because that's where the object is moving. So this is the velocity, and it's really a tangential velocity. So when you put a T in here, that means I'm talking about the tangent of the path. So there is an acceleration in here along the tangent, which could result in an acceleration in the velocity increasing in value, as I represented in here, or it could be in the opposite, where the velocity is actually decreasing. So AT could be in the same direction as BT, or opposite to it, resulting in gaining more speed or losing more speed. But then there is another component perpendicular to that, and that is what we call the centripetal acceleration, and usually we address it with a C in this case. So in addition to the tangential, there is the centripetal acceleration. And this handles the direction. So there are two types of accelerations, one that is going to change the magnitude and one that is going to change the direction. In general, you have both of them. Okay, think of yourself this way. If you go in a park, for example, and there is a merry-go-round. So the merry-go-round looks like this. I mean, I probably drew it terrible. Let me cancel that. Can I draw a circle in here? Let me see. I think I have some tools in here to draw circles. Draw and circle. Okay. That looks better than my original drawing. Okay, so, and let me go back into my drawing pen. So this is the merry-go-round. This is the center of it. So while you're standing in here, I'm going to draw here. So while you're standing in here, you are at a distance r, of course, from, I'm not talking about the entire radius of the merry-go-round. Where you are really matters, because you're the one who's going to be subject to that centripetal acceleration. If this merry-go-round is going around, by the way, this is against the clock, okay? The clock usually goes like this, okay? I drew it in this direction. Usually against the clock is a positive direction by convention. So counterclockwise is positive. Clockwise is negative. This is how people agreed on things, okay? So this is a negative direction. So I'm thinking that this merry-go-round is going positive. It's turning basically against the clock. So that is a convention that people have agreed on. So if you stand in there, and you can do this experiment actually when you go to the park tonight or whenever you have a chance. So if you stand in there, and if the merry-go-round is moving, if you don't have a grip on the merry-go-round, you're going to fly out of it. Okay, especially if it's moving fast. So the faster you're going to be moving, the more your body tends to move this way. So that is what is known as centrifugal force. Centrifugal force is really an inertial force. So centrifugal force is the one that is going to throw you out. It's similar to the situation where you're sitting in a car, minding your own business, sipping your coffee. You have, for example, a Tesla that is on cruise control, okay? And all of a sudden, something pops up in front of you. So now the car brakes, or you brake, or your driver will brake, or you're on a bus, or you're on a train, or the plane. Actually, if the plane slow down a little or something, you're going to move forward. And everything that is behind you also is going to move forward. As a matter of fact, if you're sitting in the front of the train, you're going to collect a bunch of stuff from the people sitting in the back, okay? So because the train came to a sudden stop. So what is that? Is your inertia, mass times acceleration. So here is the situation in that case. So you have a bus or train moving in this direction, and all of a sudden it applies brakes. So now the acceleration is this way, because it's braking, it's trying to stop. So the acceleration in the opposite direction of the velocity, he wants to call the velocity off. He wants to bring it to zero. He wants to stop it. So in this case, the acceleration in the opposite direction. So this is actually a deceleration. So what happened to you in here, sitting on your chair, minding your own business, watching your favorite game or whatever you're doing on the phone, and then all of a sudden, what happened to you in this case, you're going to move forward by a force called ma. Opposite to this A, but in the opposite direction. So that is really what's going on. So this is an inertial force, not a real force. It's a force, if you wish, has to do with F equals to ma, the ma part of it. So this is an inertial force. Same thing. Of course, if you have your seat belt in this situation here, if you're attached to the bus seat in here with a seat belt retained, you're not going to fly. You're going to stay. I mean, you're going to press against the seat belt, but you're not going to actually move forward. Okay, and that's the purpose actually of seat belts, to prevent such a scenario, is that they will hold you in place and you don't move forward. So in this case, what the seat belt does in this case is going to provide the force necessary to make this ma cancel. So there is a seat belt force in here, so we're going to call it F seat belt. that must be equal to ma. Because if it's not equal to ma, what happened in this case, let's say, for example, the seatbelt doesn't provide enough force, it's going to torque, and you're going to continue moving. Okay, so you really need a seatbelt force in this case to retain you from moving. This is the same scenario in this case. If you are not holding firmly to the merry-go-round, you're going to be thrown away in this direction by a force that is m times the acceleration, the centripetal acceleration. Because as you're going around the center, there is a centripetal acceleration, and that is part of F equals to ma2. I'm assuming that this is moving at uniform speed, so I'm not worried about the tangential force. Remember, the tangential acceleration is the one that has to do with the change in velocity. Let's say, for example, this is moving at uniform motion. Then in this case, this is 0, at is 0. So in uniform circular motion, at is 0, no tangential acceleration, end of the story. That's the only difference. But there will be always an AC. The centripetal acceleration always there, as long as you're turning, because you're changing direction. As long as you are in a circle, it doesn't matter if you have the cruise control or not. So if you have the cruise control on a car and you're going on a curve, that is centripetal acceleration. If you don't have full grasp on the floor, on the road, your tires and your road have enough friction between them to retain you, the car will slide to the opposite direction because of the inertia, because of centrifugal force. Now, some roads, if you noticed, actually are banked. They are curved in a sense, like, for example, the cyclists in the Olympics, when they go on those when they enter the stadium, because they're coming with very high speed, but the stadium is curved. So in this case, in the tires of the bicycles, okay, for the cyclists, for the Olympics, they're thin. So there is not enough contact between them and the field. So what they do in this case, they curve it. They make it as it's going to go on at an angle. Instead of having a flat curve, then they give you an angle. So in that case, it's going to help, because the force of gravity will also help you stay on the road. You don't slide. So again, we're going to talk about the banking of roads in this case. So in that case in here, if AT is 0, AC is still there. AC is always there. And that's the bottom line that I'm trying to argue in here. The acceleration, the centripetal acceleration, is not equal to 0 no matter what. Are you going with cruise control or no control? As long as the motion is on a circle. Is on a circle. As a matter of fact, it doesn't have to be on a full circle. It could be on a part of a circle. As long as it's part of a circle, you're in good shape. I mean, that's it. And that's exactly what curved roads are. I mean, curved roads are not circles. I mean, I know that there are those circular, what do you call them, the intersections, but you don't stay there forever. You just go around and you continue. So as long as you are on a circle or parts of a circle. In either case, the acceleration is never 0 in this situation. And what I mean by that is centripetal acceleration. So in this case, if you don't hold firmly to some sort of handles on it, and that will provide you with a force that is equal to m times your mass times the acceleration, centripetal acceleration. If you don't do that, you're going to fly away. And then also the ground, usually you have to have good shoes to firmly put your feet on it. So sometimes some people who are especially athletic enough, and if the merry-go-round is not going too fast, they could sustain themselves without really holding to something, because again, they have friction between their feet and the surface. I mean, case in point, if you make it extremely smooth, the surface, or put oil on it, no matter how athletic you are, you're going to get out of the place. You're going to fly away in the opposite direction. So that is a centrifugal force. Centrifugal force is not a real force. Okay, it's really an inertial force. Centrifugal force, not real. But how should I call it? Inertial force. That's exactly what it is. It's an inertial. Okay, just like what you experience if you're sitting on the bus or in a car and somebody hits the brakes. And it's the same thing, by the way. If you're sitting in a car and all of a sudden the driver or you accelerate, you're going to move forward because the accelerate move backward because the acceleration is forward of the car. Then your body wants to go back, wants to move in the opposite direction by your mass times the acceleration. I mean, you find yourself pressing against the seat. And if you have something hanging on the rear view mirror, you could see that too. As the car accelerates, it's going to move back. As the car comes to a brake, it's going to go to the windshield. And if you pay attention to it, as the car is going to the left, turning left, that is going to actually swing to the right. If your car is going to the right, that is going to swing to the left. It's always the inertia. But in the first two cases, as the car is moving forward or backward, the object hanging is going to either move backward or forward. That is actually tangential acceleration. In the case of going on a curve, left or right, that is a centripetal or centrifugal force in this case, due to the centripetal acceleration. In general, you could be doing both. You could be on a curve and slowing down or accelerating. So that thing there will hang not necessarily from window to window or from front to back. It's going to go on a curve, depending on which way. So it's going to be the resultant of these two forces. In general, if AT is not zero and AC is not zero, the acceleration, let me draw it with a different color. The acceleration actually is going to be the sum of these two. That is going to be this vector. So your motion will be in this direction, or the object hanging is going to be ma, this way. M times A, where A is a vector, and the A vector in this case is going to be the tangential acceleration plus your centripetal acceleration. Okay, I think we got the points. I hope that we did. If we did not, I'll be more than happy to discuss this one. By the way, this is not in lieu of reading the unit chapter. So I mean the chapters from this chapter 4. So I'm hoping that you guys will go and do the readings to understand this. Okay, let's get into a little bit more quantitatively how that means. Okay, how do we do it with numbers? I mean, we know the acceleration, what I call the tangential acceleration along the tangent, is exactly what we've been calling the acceleration up to this point, which is the rate of change, in this case of the velocity, which is in this case has to be tangential. The velocity is in the tangent, end of the story, divided by time. So if the velocity is not changing, then in this case, there is no tangential acceleration. And this picture in here goes back to just one acceleration, which is the AC. If AT is 0, then this line is exactly AC. Okay? So we don't have to worry about it. That is provided that VT is 0. VT is constant, I shouldn't say 0. Delta VT is 0. Okay? And that is what I called earlier the uniform circular motion. Okay? Now, how do we find AC? That's a good question. Glad you asked it. Let me make sure I have the correct color though. Okay, so AC is given by the square of the velocity. I mean, the derivation for it is a little bit outside of the scope of this course, divided by the radius of curvature. The square of the velocity divided by the radius. I'm going to leave it as such because radius could be two things. It could be a real circle. So in this case, I'm really talking about its radius, or it could be part of a circle. So it's really curvature. So I need to find where the center is and measure the distance from where the vehicle is to where that center is. Because a typical road, for example, if I'm really interested in it, it goes like this. So I'm going straight, and then curve, and then go straight. So where is the radius in this case? I don't have a circle, you ask. No big deal. So if the car is here, this is part of a circle. So find its center. So this extends as a circle like this, probably. So if it does, then this is the circle, the radius of the curvature, because it's not really a full circle. It's just part of a circle. So the vehicle was going for example, from west to east. And then now it's actually from south to north, okay? Depending on how sharp the curve is, R could be big if it's not that sharp, or R could be small if it is really a sharp curve. So if R is small, this is a sharp curve. You really need to slow down a lot, because if R is small, when you divide by a small number, the ratio is big. I mean, think about it. If you divide by 1, you really are going to get nothing, because v squared over 1 is just v squared. But if you divide it by 2, sorry, what should I say? If you divide it by half, not 2, sorry. So the R is small, that means you divide it by less and less. So in this case, if you divide it by half, then it's going to double. Or a better example, if you divide it by 2, for example, let's say, for example, the radius is 2 meters. And the velocity, for example, for a case of practical purposes, let's say, for example, it's 10 meters per second, okay? So in this situation, I take 10 meters times 10 meters, that's 100. 100, because I need to square this number, remember, so this is squared. Meter squared per second squared, divided by, in this case, the radius is 2 meters. Cancel the meter with the meter, and then you have 100 divided by 2, that's 50 meter per second squared. This is a big acceleration. This is 5 Gs. Remember, G is about 10 meters per second per second. 10 meters per second squared. That's a G. That's the G force. That's the one that if you drop an object, it's going to fall with it. So this is 5 Gs. 5 times 10 is 50. So this is really a 5G acceleration. It's a lot of acceleration. But if the curve is more than that, the curve is actually smaller than that. Let's say for the case of purposes, the curve is actually not 1 meter, 2 meters. So if we're going to go on a curve that instead of going like this, where this radius is 2 meters, we're going actually on a curve that's like this. The radius is just here, half that, or something that's jumping here on me because I need to. So it's half of that here. So this is 1 meter. So if it's 1 meter, the curve is sharper. So in this case, how much acceleration we're talking about? In that case, it's going to be, again, 10 times 10, which is the velocity squared. That's 100 meters squared per second squared. That's where the 100 is coming from, by squaring the velocity. Divided, instead of by 2 meters, we're going to divide it by 1 meter. Again, the meter cancels the meter, and I have 100 divided by 1, which is 100. And that's 100 meters per second squared. Remember, G is always 10 meters per second squared, never changes. So this is G, and this is the centripetal acceleration I'm talking about. So this centripetal acceleration in the first case is kind of small. I mean, it's big. 5 Gs is big, but it's not as big as 10 Gs, because this is 100, which is 10 times 10. So AC in this case is actually 10 Gs. So in other words, as the curve becomes sharper, the acceleration becomes bigger. So really, the force becomes bigger too to throw the object is. So sharper curve will result in a higher centrifugal force. So in either case, you really need a lot of friction or retaining walls or bending the road enough for the object not to fall. And this case in here, for an object moving with this velocity, depending on how much it is, the closer you get, the higher the centrifugal force. In this case, the further you're going to get from the center, in this case, the less the centrifugal force is. So if the object is moving super fast, or one way actually to counterbalance that is move back to the edge of the merry-go-round. Okay, then you will have less force to contend with because R becomes bigger. But here, the situation with the merry-go-round is really not that sensitive, honestly, more to the distance because of the fact that it's a small enough object. The change in R is not big enough to account for it. It's the change in V that matters. So what's going on in here? Let's say, for example, some crazy dude comes in here with a speed about 20 meters per second, decides, you know what, I'm going to go with this this curve in here with twice the speed. So what's going to happen in that case? How much force is he dealing with? So in that scenario, here is a problem. So if that person, we're going to call him Crazy Joe. I don't mean anything by it, so please don't refer to any political thing or anything like that. The radius in the first case, we said it's 2 meters, okay? So the acceleration for this curve in here, the acceleration, centripetal acceleration is going to be this number squared, which is 20 times 20 squared, which is, that's what it is, divided by 2. So if you do the numbers, 20 times 20 is 400 divided by 2, that is 200 meter per second squared. Again, this is about 20 times G's. So this is a lot of acceleration, really. So if this car, for example, weighs a ton, all of a sudden now the force is 20 times bigger, just because he doubled the velocity. Let's say the speed posted on that curve in here is 10 meters per second, and the person comes in with twice that velocity. He really needs a lot of friction to hold them in place, or a lot of bending of the road, with gravity to hold them also in place. So this is really what's going on in here. If the curve radius, if the radius is actually curved differently, 1 meter per second, 1 meter, I'm sorry, and the velocity is still 20 meters per second, then how much acceleration we're talking about in here? So again, it's going to be 20 times 20, which is what 20 squared means, divided by 1 in this case, and it's going to be 400 meters per second squared. Now you're talking about acceleration that is 40 Gs. I mean, even astronauts, I mean, when they experiment, when they do their training to go into space, they really don't experience this acceleration. These numbers are ridiculous. I mean, in a practical examples, these numbers, you don't encounter them. Although briefly, you might be subject to a higher acceleration, but for a short period of time. Remember, astronauts, they get trained for this higher G values because they're dealing with tremendous amounts of acceleration over a long time. But usually for our cases, this is a short period of time, but even this acceleration, they can be dangerous to a human being because they can result in physical damage to a person that is beyond repair. And this is if it's not bodily injury immediately, you can have concussions, you can have all kinds of things. I'm not suggesting you do that. As a matter of fact, curves are not really 20 meters, I mean, 2 meters or 1 meter curve. I mean, that is ridiculous for a car. So practically the curve, the radius is far greater than that. It's several tens of meters, okay? 20 meters, 30 meters, 50 meters, and the wider the curve, the higher the speed. That's why freeway curves are usually much bigger with a bigger curvature, because cars are expected to be moving faster than street curves. And street curves, even that, to begin with, the street speeds are a lot less, and even on the curve, you can't really go that fast. You have to go slow, otherwise you're going to roll and fall in the opposite direction. So that's really what's going on in here. So these numbers I throw in here just to simplify things a little, but they're not practical. Okay, so in a sense that when you're doing this, you have to be careful with it. The point I'm trying to say in here is, now we have graduated the one-dimensional motion. Now we are talking about more than 1D motion, and we started with the circular motion. Circular motion shows us acceleration in reality. And acceleration in this case has 2 components. In more general cases, this could be far more complicated. Okay, so for example, for the weather phenomena, you could have all kinds of accelerations. Some of them are inertial, most of them are actually inertial in most cases, but some of them are actually tangential or linear. Okay, they have to do with the increase or decrease in magnitude. And I'm thinking in terms of the Coriolis force that is responsible, for example, in the case of the hurricanes or in the case of the toilet and things like that. That is actually another type of inertial acceleration. So acceleration in general can have many components. In this case, for the circular motion, it's a vector that is the sum of both the one along the direction of motion, that's what the tangent means in this case, plus the one that is normal to it. So this is in the case of a circular motion. I mean, adding vectors is a very complicated thing to do, but that's basically in a nutshell what they are. In our example, in this case, what a vector is, that's why we really need vectors, because here is the question. Let's say, for example, we are this is our origin, and a person decides to wander around 5 meters away from the origin, and he decides to move away another 5 meters from the origin. I mean, if the motion is on a linear motion, the person could end up easily at 10 meters away from the origin. That's no complicated scenario. The other problem is a person could actually end up in the origin by going 5 meters and coming back 5 meters. So the problem is kind of simplified in this case because the person really is back to where he started from. Or the person could have gone 5 meters this way and then came back 5 meters, or 5 meters is the opposite. So in the one dimension, really, we don't really have complicated scenarios. But if the person is wandering in space, then the problem is far more complicated. The person could have gone from the origin and wandered 5 meters and ended up in here, which is at a distance less than 5 meters because he went on a path that is not. So here is where the 5 meters is. But this person ended up in here, which is a distance a lot less because he went on a path that is not regular. And then the next day he went on a different journey and ended up somewhere else too, because he could have wandered this way and then ended up in here. So the path could be far more complicated when it's in this scenario. So what we do in this case, we use vectors. So what a vector is, a vector has two quantities, a magnitude and direction. This is on a two-dimensional surface again. On a two-dimensional surface, it's still kind of easy, a little bit, honestly, because we don't have to deal with another dimension to worry about. In a two-dimensional motion, this is usually the east-west or west-east in this case. So this is the east, and that is the west on the opposite direction. This is labeled usually the x-axis. And the south, coming from south, going to north, that is usually labeled the y-axis. So a vector in general, whether this one or this one, has two things: how big it is, that is the magnitude, and also the direction. So what we mean by direction, it's usually by convention. Again, when we say convention, it's people agreed on it. It's the angle that is made between the x-axis and the vector itself. That's the direction. So it's an angle in degrees. So the direction is the angle between the vector. No, I should say, no. It has to be very careful, because remember that I mentioned earlier about the positive and negative directions and all of that stuff for the rotation. By convention, counterclockwise is positive and clockwise is negative. So I have to really be technical in this case. So I'm sorry about that, but we have to say it correctly. Between the x-axis and the vector, not the vector and the x-axis. And the vector. So it's always from the x-axis to the vector. So in this case, the way I drew it is correct. I started from the x-axis and it went counterclockwise until I hit the vector. That is my angle. Same thing in this case. It's not this angle, the direction. It's this angle is the direction. It's more than 90 degrees for the second vector. So this is correct, the way I drew it, but I'm going to draw something that is wrong. Okay, this is not direction. It's incorrect. This is not the direction. This is not correct. This is not even the direction. This is not correct either. The only way that is correct for this vector is the one I drew earlier with the red marker, red pen, that shows from the x-axis going against the clock to the vector. That is a convention. That's what people agreed on, what vectors are, okay? At least in 2D. Okay? In 3D, you have to define 3 axes, actually, to define the angles. And the angles, there will be 2 more angles for a given vector. So in 3D, actually, the problem is more complicated. And we're not going to be doing 3D in this class. This is outside of the scope of this class. So when I say multidimensional, I really could have said just 2-dimensional. But in general, we're talking in multidimensional. Now we're graduating really the 1 dimension. Okay, so that is really what we have in here. I know for some of you, this is a lot to take, okay? And for those, I know this is probably have seen it before, so it's not really big deal. But I really want to stop here today. The reason why is because we're going to be talking about the other kind of motion, namely the, and I'm going to introduce it actually, namely the, because we need it today, actually, namely the projectile. And projectile is another example of a two-dimensional motion also, which is a multi-dimensional motion. Okay. So what's going on in the case of the projectile? You have an object that is thrown not straight up and down, like we've been dealing with for the case of the free fall. For the case of the free fall, I take this object and I drop it, and that is a free fall. But for this purpose in here, we're going to throw it at an angle. So this is the x-axis again. We just defined how the axes are presented, and this is the y-axis. In this situation, it's not from north to south, but it's from down and up. Okay, so this is the lower, so this is the ground, and this is somewhere up where the object would fly. Okay, so below the ground is somewhere in here. So in other words, you could actually go on the top of a building and throw an object on a curve. That object will follow projectile, but it's not going to come back to your ground, to your level. It's going to come back to the ground, which is below you. So in that scenario, you could be here. So you could go to a top building and you throw an object, and that object, you throw it at an angle. So it's going to come back in here and fall to the ground. Okay. Similarly, actually, you could dig a hole also on the ground too. You could come in here and have a hole on the ground. Okay. So this is your ground level. So as you throw an object from here, it's going to go and follow a curve, but doesn't fall to the ground because there is no more ground in it. It's going to fall to whatever below area that you have in here. So again, this is what projectiles are. So projectile is a motion in two different axes. It can be broken down into a motion in the x-axis as the object is moving away from you, from the source, and also up and down motion. So this is a two-dimensional motion in this case, but in general, it could be more than that too. In general, it's a multi-dimensional motion because the object could be drifting also due to wind, going east-west. I mean, north-south, for example. So you throw it up, intending it to go to east, but you find it drifting toward the south or toward the north, depending on which way the wind is blowing. So the motion could be more complicated in general, okay? But we're going to stick with the ideal case. First of all, we're going to ignore air. So there is no air resistance, okay? Again, you see the approach in here. We're going to make things complicated, but in piece-wise approach, in a sense that we're not going to start from the get-go and make it all complicated, because then you're going to be dealing with other forces like the drag force and all that stuff. So at this point, that's all we're going to be focused with is this scenario in here. So yeah, we moved a little from the 1D, but we didn't really move all the way. So we're just somewhere in between where we're going to neglect stuff. So in this case, here is what determines the projectile. The projectile has a velocity vector that looks like this initially. So this is the x-axis, and this is the y-axis. So the velocity, this is called the initial velocity, by the way. V naught is initial velocity. So you're asking me, how much is the initial velocity? It is the magnitude of V naught. So this is the speed, initial speed. But then I need to know its direction. Because if I throw it up and down, straight up, that is actually not a two-dimensional motion. If there is no air resistance, it's going to go straight up and come down. So that's actually a one-dimensional motion. If I throw it, for example, parallel to the x-axis and stay parallel to it as much as I can, then in this case, if there is no gravity, it's still it's a 1D. But if there is gravity, actually, it's going to bring it down further. Okay, so you can't really do that scenario. So the point being in here is this direction is needed. And here is, again, I just mentioned how the direction is defined. You start from the x-axis and you move toward the vector counterclockwise. Because somebody else might say, you know what, I can do this. And you're right, you can do that too. You can go with the clock, start from the x-axis, no big deal. I'm going to start from your x-axis, but I'm going to follow the clock. This is how the clock ticks. And I'm going to come back in here and meet the vector v and tell you that this is direction. This is wrong. Why? Because you're going in the negative direction. It has to be in the positive direction to really matter. So you really need to start from the x-axis always. And don't stop until you hit the vector first time, because somebody else might say, you know what, I could go, I met it already, but I don't care about that. I can meet it again. And then that is going to be my direction. But that's an indetermination, because how long then you're going to be stopping. The convention is only the first one matters, okay? Because all of the other directions are the same. In other words, if you find that the direction is 30 degrees, for example, 30 degrees plus 360 is the same thing, which is 390 degrees. It's the same thing. So in directions, whether it's 30 degrees or 390 degrees, or for matter, 780 degrees. How much is it? Oh, wait a minute. Yeah, 750 degrees, I should say. 360, 720. Yeah, 750 degrees, it's the same thing, because you go twice. 360 and 360, that's 720, and add to them 30, that's 750. So you could go as many as you like, as long as you are in positive direction. So it's still positive. So in this case, you're good. So the direction is not the problem. The problem is the value, because you may say, okay, is it 30 degrees or is it 390 degrees? And I'm saying in here, it's the same. Okay. But usually we take the first value in here, in this case, and say that's the direction. 30 degrees is good enough. That's the direction of the projectile. So this is what we call the direction of the projectile, the initial velocity with which you throw the projectile. So in that case, what's going on in here, there are two components to the vector velocity. There is the x component. This is the horizontal component. But also there is this component, which is the vertical component. Now, projectile has some characteristics. First of all, the maximum height it's going to reach, and that is determined by the vertical component. The bigger the vector component, the higher the object is going to fly. That's it. And then there is the range, and range is how far on the x-axis can it go. So this, if you throw it, it's probably going to go like this and fall somewhere in here. This distance is what is known as range. Okay. So that is some of the characteristics of the projectiles. Another characteristic which is important is the time of flight. Basically, how long for the object to remain in flight altogether, from the ground back to the ground. And you can think of it as basketball players when they jump to try to score a hoop. So when they jump, they're flying. So for a moment, they're actually in the air. Okay. For a moment, they're suspended in the air. That is the time of flight, how long they're going to stay suspended. So these are some of the characteristics of the projectile motion. When we come back on Wednesday, we're going to get into a little bit more details of these things. And also, we're going to actually talk about these things this Wednesday. I mean, today. I'm sorry, today. We have the problems on this afternoon. So we're going to go and cover as much as possible from those problems. I know there are a lot, but I'm hoping to cover a lot of them. And should you have any questions, please do not hesitate. Again, you're going to be tested on these things, so you better really have to have full grasp on these things and understanding on how they work, not only in terms of conceptual wise, which is part of the exam similar to exam 1, but also quantitative wise, basically being able to analyze and come up with answers to problems similar to the homework assignments that you've been dealing with. Sounds good? Okay, so I'll see you guys later on in the day, 12:45. Thank you.